Hello everyone, so today we're going to be using the result from the equation that we just derived with the resistance of B2, and we're going to derive an expression from this for the overall resistance of a pipe, a radius R1, wrapped in an insulation of a radius R2. So what does this problem look like? So we have our inner circle, and we have insulation wrapped around it. So this inner circle, this will be R1, and then the radius of the insulation is R2. So we have cold air on the outside of this pipe, cold air, and we have warm air on the inside. So to try to find a resistance total, use a different color. We recall this is our conduction plus our convection, or resistance of conduction and our resistance of convection. So what is our resistance of conduction? Well, we just derived it, and it's equal to natural log of the bigger radius over radius 1 all over negative k 2 pi and the height 1. So, little reminder here, h1 is equal to height, just so we don't get confused in the future. So we have our conduction. Now we need to find our resistance of convection. So what is our radius of convection? Well, we can first go back to our heat transfer of convection. So Q of convection is equal to the convection coefficient, area, delta T. We recall Ohm's law. We have delta V equals our current times resistance. So we already have our delta T's, so we can rearrange this so the delta T is focused. So we have our current, our voltage, our difference in voltage, and we have our resistance now. So our resistance of convection is 1 over HA. Now H is not height, that is our convection coefficient. So we still need to figure out our area on this. And our area of convection is 1 over 2 pi R2 and then height 1. So now we can add these all up together to try to figure out. First we'll write out our convection, which is 1 over h 2 pi R2 h1. So now we can add these up together to get our final equation. So our total is equal to ln bigger radius over smaller radius, negative thermal conductivity times 2 pi h1 or height, plus 1 over h or thermal convection coefficient, 2 pi R1 or R2, times h1 or height. So that is our formula for our total resistance of a pipe of radius R1 wrapped in insulation of radius R2. Thank you very much. Hello everyone, so today we're going to be determining the expression for the first and second derivatives of the total thermal resistance that we just obtained in the last portion of this video. So first remind ourselves, what is our total? And R total is the natural log of the radius 2 or radius 1 over the thermal conductivity times 2 pi, the height, and then that's plus, and then we got the thermal convective 1 over the thermal convective component, and then 2 pi R2 with height. So first, we want to take the first derivative. First, you're going to move out the constants of this one. So our constants here is that 2 pi h1. So we're just going to separate that out from this. I guess it's 1 over 2 pi h1. So we are more worried about the other values. So with the ln R2 over R1, we get 1 over R1 times R1 over R2. And then additionally, we have that K value. And now this is positive now because that negative came in. So negative times a negative equals positive. Additionally, on the other side of this, a reminder that 2 pi h1 is out. And we're just taking the R2. So we have 1 over R2, which gives us a negative R2 squared over 1 over h. So our dr total, canceling these out. Sorry, excuse me, that K is on the bottom. So our first derivative looks like so, where we have 1 over R2K plus, or minus 1 over R2 squared H. So that's our first derivative. Now, to take our second derivative, we have the following. So we have D squared R total over dr squared. We'll get the negative back in our value, R2K, and then plus 2 over R3H. And that is the second radius as well. So that is our value for our second derivative. Hello everyone, so today we're going to be going over the practical consequences of our C2 and C3 solutions, and why is there a minimum value for which R2 and adding insulation has the actual opposite effect of the intended purpose of it. So first we're going to start off with our original equation for the R total. So over here. So if we recall back to what R total was, we have ln R2 over R1, our negative K value, and then 2 pi H1 our height, and plus 1 over H our thermal convection coefficient. And we have 2 pi R2 H1. So what we're first going to do here is we're going to set this equal to 0. And then we're going to take the derivative of this equation. So we're going to set this to 0, and then take the derivative of this. To where we get 1 over R1, then R1 or R2, and then times negative, or not negative, that's negative K 2 pi H1. Now the other side, we get minus 1 over h times, not 1 over h, sorry, 1 over h2 pi h1 times negative, not negative, sorry, r2 squared. So we got the negative there. So now we can start to simplify this a little bit more. It's also going to be equal to 0. So these r1s cancel out, and so these negatives cancel out as well. To where we're left with, as you know, 1 over r2 k 2 pi h1, or height, minus 1 over our thermal convection coefficient, 2 pi h1 and r2 squared. So that is our derivative that we have simplified. We're going to set that equal to 0. So now we can put these on either side of each other. 1 over r2 k 2 pi h1 equal to 1 over h2 pi h1 r2 r2 squared. So now we can start to do some canceling out, and this 2 pi h1 immediately cancels out on both sides, to where we have 1 over r2 k is equal to 1 over r2 squared h. So this r2, one of these r2's will cancel. We'll have 1 over k is equal to 1 over r2 h. So to get this r2 alone, r2 will be equal to k over h. So now we have an r value for r2. So we're now, let's take the second derivative and then input this. So we'll put that right up here. And taking the second derivative of our equation, if we remember back from our original video, our second derivative, or the last video that we just had, so our dr total was negative 1 over k r2 squared and plus 2 over r2 cubed h. So now we have actual values for the r2 values, so we can input this r2 value back into the equation. So this negative 1 k r2 squared becomes kh squared and plus 2 over this kh cubed h. So what does this become? So this becomes negative 1 over k to the third h squared, and then plus that k to the third 1 over k to the third h squared. That's 2. So this equals 2 at h squared is up top. So that's minus 1, so that just equals h squared over k3. So this is actually positive, so now we can write our graph, and we realize that since this is positive, that it will be concave up. So that means our point that we just established there is actually below the starting point at which we have. So to give it some frame of reference, I'll draw a graph down here. So we have our starting point right here, and then we'll have this value right here, which is actually our R2 value, our critical point. Excuse me, that's our lowest point, and then our critical point is on the other side, to where our insulation is actually helping us not lose heat in this. So this lowest point right here, that R2KH, is where it finally starts trending up. Our value is concave up because of this positive value. So in essence, before this critical point right here, if we weren't putting enough insulation down, we were actually losing heat more dramatically than we would be containing the heat from our insulation. So there's not really too much we can have, but there's definitely not enough that we can have there. So that's the consequences of the derivations I made in C2 and C3, or C2 and C1, excuse me, and why there's a minimum value. The minimum value is R2 over KH. And after this critical point, we're actually starting to contain heat as opposed to losing it. Thank you very much.